Okay, thank you. Thank you for having me. So this talk is about stream fusion and stream processing. So stream processing is a very, very wide area, and let me give a few examples. So this is the first data processing computer. This is the computer designed by Hermann Hollerith for processing census data in 1890. Well, you probably know that the company that Hollerith founded later became IBM. So it's processed data on the punch cards, like these ones. So on the up part, these are punch cards used by Hollerith, well, according to Wikipedia. So the census data were recorded in different columns and using these holes. And on the bottom one is the modern punch card with 12 rows and 80 columns, such that I had, when I started, I had lots of experience in this kind of cards and even still remember the code. For example, this 12.1 is the encoding of A, for example. And so I can still remember some code. So the Hollerith machine did work this way. So it took the operator took the card, put it on this pad, then put the top thing down. Then there is a small needle so that they made a contact with the pad, and according to if there is a hole, then the circuit was made, and some of the dials were advanced. So this the process. This first business computer illustrates very well what stream processing is all about. So first of all, we process one card at a time. Take one card, take another card, and so forth, so forth. So the processing is done sequentially. Also, when you process the card, there's some small amount of processing is done, and the dials are a little bit advanced. So the processing is done incrementally. Also, you can process as many cards as you got. So there is no physical limitation how many could you do. And you process in a very limited amount of memory. So all these dials that you see, that's all the memory that you got. So back then, so these are four things. These are characteristics of stream processing. Well, back then, it was the only way of doing processing because there is so little memory. So little memory was there. Well, later on, memory got increased, then different processing mode became possible, like the program reads some data, then does computation for a long time, and maybe prints something. But stream processing never quite went away, so it always remains. And let me give an example. So there is a note published by Tony Hoare in 1977 about Michael Jackson design technique. So in this note, Tony Hoare described the technique and described it theoretical and proposed the notion of program traces. And as people later say, that was a precursor for his communication sequential processes. So in this paper, actually, the reproduction of Tony Hoare paper with a preface, there is a scan of the early. Why is it advancing? There is a scan from the. I don't know why it keeps advancing. There is a scan from the Michael Jackson's course notes. So Michael Jackson was the person who proposed this technique, and he was a business consultant. And there was one of the problems, which is also analyzed in Tony Hoare's notes. So the stores section in a factory issues and receive parts. Each issue and receipt is recorded on a punch card. The card contains the part number, the movement type, and the quantity. The cards have already been copied magnetic tape and sorted. The program is to be written will produce the simple summary of the cards. And here it is. And there is some quite statement at the end. No attention need to be paid to such refinements as skipping over the perforation at the end of the sheet of the paper. So as you can see that, it was one of the typical problem of the day. So it was punch cards, at least virtual in the tape. You read the tape and one by one and produce some kind of other output. And in fact, the prologue or COBOL, programming language COBOL, was designed specifically for this kind of processing, tape in, tape out. And well, speaking of COBOL, that's where the first mentioning of streams in computer science came in. It's in the paper by Melvin Conway, Design of Separable Transition Diagram Compiler, that says compiler. So the paper presents the design of COBOL compiler for the subset of COBOL on moderately large computer. Well, by that time it was, well, 16,000 words. And the compiler that the paper says, the compiler is written assembly by 2 people in less than a year. So the first section after the introduction, the first section of this paper is, by the way, the paper is available for free at ACM. So if you just Google, then you can download it for free from ACM. It's very well worth reading because it's, well, I mean, as you can see from the title, coroutines. So it's the paper, not only the first presented coroutines, and also, I mean, as I'm going to show, it also talks about the streams in modern way. So the separable program, it's the design, is the program organization is separable if it's broken up processing modules, which communicates according to the following restrictions. So only in discrete items of informations along fixed path, and the entire program can be laid out so the input is in the left extreme, and as the output is on the right, goes onto the right. And all information flows from left to the right. So this, I mean, I know basically what I said before about incremental processing and limited amount of memory, but now it's done. It's spelled in, I mean, I know, put in words. And the paper also contains this picture, which is, well, that was a scan I tried to, I mean, I know, cut and paste and reproduce, but I mean, ended up with some very fuzzy picture, but it gives the out, I mean, on the right shape. So there is a 2 modules, A and B, and these are coroutines. So depending on the resources, you can run them either connecting with the output routine right on the magnetic tape, and then with another module, read the tape and, I mean, feed into module B. Or if resources allow it, you can connect them, I mean, immediately, and they can, I mean, I don't know, call each other, I mean, module A just can pass data to B directly by calling it directly. So it's a very, very good picture, and we'll come to it later. But incidentally, can you tell that Jackson wasn't an electrical engineer, but Conway was? Well, that the Jackson wasn't electrical engineer, it's known for a fact because I read that he and Tony Hoare read classics at Merton College in Oxford, and then somehow got interested in programming. And Conway, I don't know for sure, but it's very likely that he was an electrical engineer. But what tells, I mean, me why, I mean, I think it was electrical engineer that, well, in Jackson, as you can see, there was at the page I showed earlier, there was a diagram and information flows from top to bottom. And in Conway, as in all, I mean, you can see information flows left to right. As in all electrical diagrams, the information, I mean, they're all drawn that data flow left to right. So you can kind of, so what was new? So, so he talked about sequential and incremental and processing, but also in this picture show there is something new. Then if we have those boxes that connected, I mean, that had this particular property, they do incremental processing, read a bit of input and produce a little bit of output, then can be hooked together and can be made a diagram. So there is another thing that we can create bigger and bigger diagrams with information flowing from left to right. So now we can hook them. And if we can hook them, then we can do, I mean, hook many boxes. And this is a slide that I took from Mark Puzet's presentation about synchronous languages at Stream. And then this shows a quite more elaborate diagram, which again, boxes connected with lines. And well, this undoubtedly electrical engineering diagram, because you can see inputs is on the left and outputs it's on the right, as you would expect. And it's, I mean, I don't know, but the data, there are no cycles, directed cycles. So indeed, all the data, I mean, goes left to right, but there are also, I mean, its diagram is nonlinear. There's also forks and there's also joins. Things. So this is the, I mean, I don't know, more elaborate electrical engineering. And according, if, I mean, I don't know, I understand French correctly, that is some kind of control diagram. So Merpuzet says it's an autopilot diagram, or at least part of it. And well, coming back full circle from computer science to from electrical engineering back to computer science, so maybe business. This another example of string processing is the Nextmark. It's a query 7 from the Nextmark benchmark. So monitors the highest price currently auction, every 10 minutes return the highest bid and the an associated item, the ID, in the most recent 10 minutes. And here is how this query is expressed in one particular query language. So here, I mean, I know different instance of stream processing, kinds of sensor monitoring. So we have sensors, which, I mean, here stock prices in auction or stock prices and so forth. And we, I mean, performing, I mean, processing events as they occur, or, I mean, correlating several events if there happens to be. But here it's explicit is the window processing. So the process not, I mean, just one item at a time, but some items in a particular range. And here it's a range of 10 minutes. And this is, I mean, you know, example of a very popular query nowadays is such that high frequency trading. So to summarize what is stream processing, so it's indeed very wide area. So we can see from COBOL write processing, record in, record out, then from coroutines, from digital signal processing, and event processing and correlation. And all of the things can be represented as diagrams of connected boxes with data flow left to right. There's also a trade-off. So the diagrams, of course, are very intuitive and very easy to build and very easy to read and modify. But what about performance? So some of the things, for some of the things, performance matters quite a bit. For example, for high frequency trading, then, I mean, you know, trading really has to be performed with high frequency. So how do we get from intuitive diagram to highest performance? And one of the main ways of getting it is stream fusion. So stream fusion is a very simple idea. Well, this is the diagram I took from a paper on server and stream optimizations. So we had two boxes, A and B, connected with some line, and stream fusion is just removing the line. Well, as you can probably guess, that anything that looks so simple is going to be very complicated. And it sure is. And so I'll show several examples how complicated it can be. But first, let me bring back this picture and say that stream fusion was already thought up by Melvin Conway back in '63. So at the bottom of the picture, so there's two programs, A and B, well, coroutines. So if you don't have space to run on the computer to run both of them, then you link the program A with the output routine and run them on computer, and it would create write on the tape. And then you link the program B with the reading routines and run them on the computer, and then it would read from the tape. But if your computer has enough space that it fits both programs A and B, you can just dispense from the tape and you can run them on the same computer where program A would invoke program B with the data, program B would do something that, and we need more data, then it would call program A for more and would change this. So as you can see that if the programs are written correct way, and Conway explains what is the correct way and how to program it, then if there is, I mean, enough resources that we can dispense from with the tape. So we remove that communication path between them, or all intermediate data which the tape represent, and and run directly. So that's the example of stream fusion. So the line between the processes represents communication path and maybe unbounded, in this case, amount of data. And by fusing them, then we remove them, the data, and make things much faster. So let me give another example of stream fusion and stream. So when I talked about stream, the example of Unix pipes probably occurred to you already. So this is one of the examples of Unix pipeline. So you probably guess what it is doing. Well, if we disregard the cat, then tr minus d, it removes underscore, then tr translates uppercase letters to lowercase letters, and then we search for flatmap, and we count the number of lines that contains the flatmap. So this is the, typical Unix pipeline, and it's rather intuitive. Well, according to McElroy, when he said that, he wrote in, I forgot, some history of Unix, then when Ken Thompson implemented pipelines, the next morning, everybody was writing, pipelines such like that. Everybody from all the departments, including secretaries. And of course, the mention of secretaries was, important because Unix was initially done as an office machine for people in the patent office for creating documents, which are, doing string processing and performing formatting or querying, something like that. And secretaries indeed found this very intuitive and very, really helpful, and they were very enthusiastic about Unix. And they told that the enthusiasm to their bosses, and the management took notice and continued funding development of Unix. And according to McElroy, that the ease of formatting, including the pipelines, was one of the deciding factors for success of Unix. So, despite of Unix many drawbacks, and this is a pipeline illustrates this one of these drawbacks. You can see how many processes there are. So there is, well, if we disregard cat, we have tr, we have another tr, we have grep, and we have wc. So each of those programs is a separate Unix process. It takes resources because it needs its own heap, it needs its own stack. And there's pipelines between them. It also takes compute resources. And each of them performs rewriting of data from one to another, from one to another. So it actually becomes quite expensive. And even nowadays, when the system have lots of memory and high performance, if you compile, for example, GCC or some other compilers, which often rewrite when use pipelines in the build process, the slowdown is actually quite noticeable. And it can be slowed, these processes can be removed because all the processing can be done in one step. And here's an example in awk. So if we remove, again, we don't count for cat, then we can, in only one step. And of course, the saving is significant. No longer there is only one process instead of 4. There is no need to replace something and rewrite one string to another instead of all done just reading of the string and matching. There's nothing needs to be, no rewriting needs to be done. So there is significant savings. It also from this example that transforming, although the bottom fused example is, much faster than the pipeline, it's also much difficult to read. And it's probably not something that you immediately occurs to you that to write in this way. But yes, the point of both examples is to match for flatmap regarding of the case, and probably with underscores occurring at any place. So what I actually, the example that what I've been talking about in pipelines and Unix pipeline and fusing it, it actually wasn't a kind of idle talk. This is exactly the argument for Perl. Because as I recall in the 90s, that's how Perl was marketing. So instead of writing pipelines which have poor performance, just write everything in a single language, write everything in Perl. Okay, and now we get to the next example, which is the topic of this lecture, close to the topic of this lecture, and also relates to the topics of the previous lectures. So this example of array, and well, I mean, this seminar is about array programming, so there is something that you've seen before. So suppose we have some array A, and we want to compute the sum of squares of its elements. Well, because we wanted to find the values, for example. And also this is one of the popular benchmarks. So I'll write this processing in OCaml because it suits me, but kind of similar processing can be done in MATLAB or similar code in MATLAB or NumPy or, I mean, Julia or any other language. Well, in MATLAB, you don't have to have a map. So suppose I have some function square, that squares element that maps, that applies the function to each element of the array. And again, in MATLAB, map is implicit and has to be written. And the sum is some function that sums all elements of the array. Well, I mean, it's, as I said, it's easier to write in any language, and it's easier to write also in OCaml because, well, I mean, all these functions essentially standard library functions. So because I don't actually need this intermediate A2, so I can write this in one line. So map square of A and then sum. So now it's, I mean, if we simplify it further, then we probably get something similar to APL. But in mathematical notation and also in APL on which it is based, the information flows right to left, right? So there is A, which is then it goes into, I mean, map and squares, and then the result flows into sum. So, but it's kind of unnatural. I mean, giving all the previous talks about left to right, then it's kind of more natural to me, even I mean, to me, now the more natural right to left, left to right flow of information. But we can fix that. So we defined an operator, which is an application with flipped arguments. Well, in fact, OCaml standard library already defines it. So then we can write the processing, I mean, as shown on the slide. So I hope that, I mean, that reminds you of something. And it not only feels like a pipeline diagram, I mean, it not only looks like a pipeline diagram, it also feels like, but because it's very easy to extend. For example, suppose in our array, for some reason, has nuns. So then those nuns are going to throw a wrench into our calculations. Actually, I already forgot what MATLAB does in this case. Probably does nothing, and therefore the result would be none. So if we have a filter function, well, don't look at the gray parts, then we can perform filtering, enter filtering into the pipelines, and to filter out all nuns and infinities, and perform the rest of the calculations only with the numbers that were left. So that's very intuitive, and this is the very nice way of developing computation. Little by little, we adding steps and see what the result is. That's, of course, I mean, all very nice, but undoubtedly you have looked at the gray parts and were horrified. Because, well, even, I mean, map, I mean, according to, I mean, array signature, it reads it takes an array and produces an array. So it, I mean, it produces an immediate array, and then some deconstruct this array. So even in this part, there is already intermediate array, so whose size is equal to the size of the input array. So there is no bound. So it's a well, it's a linear in the intermediate array, in the linear in the size of the input. And if we look at the filter, then it's just horror, because there is so many, intermediate data is created and destructed, and with a size which is proportional to the input. So for a very big input, then it's going to be a big problem. So again, it looks very nice, but performance is horrible. So what can we do? Is there anything? Well, we can just change the representation of the arrays. So we can represent the array in a more abstract way as a combination of a shape of array, or in this case, just for linear array is just a number of elements, and the content of the array. And the content is the indexing function that takes an index and returns the element on this index. So this is a very, very old idea, goes back to an initial implementation of APL. So initial APL implementation already had this idea. And it's used in, I think, to my knowledge, in every array language. And I think it, in my knowledge, is used in SAC or SAC. I forgot how it's actually pronounces. So given normal array, it's very easy to convert normal array to this more general array. So the size int, so the shape is just the length of the array. Indexing function is array get. For the mapping function, so again, if I define this combinator to be a left to right composition, then mapping is composing indexing function with a mapping function. Notice that now map has a constant type processing. It doesn't create any arrays, doesn't create any data structure. It just takes the function, composes, immediately returns results. So it runs in constant time and constant space. Well, summing function, well, since we have all needed information, we have the number of elements, we have an indexing function, then it's very obviously we can sum all elements together. So there is no longer any intermediate array creating. So all the array, the initial array which was there, array get and in memory, and we're just using these elements of the array as they are, transforming them on the fly as we do. So it's all, we've solved the problem of intermediate data structure of unbounded size. So it's excellent. But, so we write pipelines as before, and it now runs much faster because of the data, in constant memory. But of course, there is a problem then how to do filtering, how to put filtering in there, how to accommodate filtering. Well, to accommodate filtering, we need to change our representation, augment our representation a little bit by accounting for missing elements, which are modeled in an option type in OCaml. So some means the present element and none is the absence of the element. So this is also a very, very old idea. It's present already, it was present already in the language Lustre, in the synchronous programming language Lustre, and a lot of work in stream fusion and Haskell and so forth that uses exactly the same idea of stream with missing elements. So our previous combinators had to be accommodated for the missing. Well, to array is very easy to accommodate. Well, look at map. So map is, so if the element is present, then we apply mapping function to it. And if the element is not present, well, it remains non-present. It remains missing. Then sum has to be accommodated. So if there is, missing element, well, there is nothing to do. We just ignore it and keep going on to other elements. And filter, well, so if the filter takes the predicate and applies it to the element and the predicate returns true, then the, so if the element is present and the predicate returns true, then, well, it remains as it is. And if in all other cases, the element missing. So the missing element remains missing. In addition, if the predicate fails, then the current element becomes missing. And now we have achieved fusion, so we can now even write with a filter, and we have no unbounded intermediate data structure. But not everything is, so there is a fusion, but the fusion is incomplete. For example, look at the map. So it's, I mean, each element, so we perform matching, and so deconstructing this and get sum, for example, see sum, and then immediately create a new value of the option type with the sum. So we deconstruct and construct option values of the option type. So we remove the constructor sum and add constructor sum. So there is still intermediate data structure that, I mean, created and removed in the process, whose size is constant, so not unbounded. It's a constant size, but there is a, I mean, it is an overhead. So there is another problem, is there is a many function calls per operator, right? Because the map is, I mean, performs when indexing has to perform function call for fx, and I mean, so there's a lot of first class functions, and there is a lot of calls, which is, I mean, not very good, because I mean, calls in a tight loop has a very bad performance. And of course, it's a, I mean, obviously high order processing, and so how to do it in, for example, in hardware, in the FPGA or in the C, etc. So, well, we can do it by treating missing elements in a little bit different way. So now the indexing function also returns, takes a continuation on what to do with the element. So if the element is present, then it passes to computation to do something with it. And elements, it turns out missing, then we do nothing. And for the nice thing for it to work, then it's useful that the whole computation itself, I mean, returns unit. So in a sense that we are moving into imperative realm. And if we move that, then things become quite easy. So it's indeed, we just do nothing. And I mean, if there is an element, then it will do something and update the state. So the function toArrays becomes, well, it takes now continuation, and then we get the element and just pass it to continuation. The map, well, I mean, similar to, well, it's kind of functional composition, but in continuation passing style, so there isn't anything. And for float, because now we need to have some processing which it's imperative, then we write it the imperative way, so with a for loop and accumulating in some sum. And indeed, now we can see that if IX produces the element, it's passed to the operation that updates the accumulator. And if IX misses, if the element is missing, then IX simply, I mean, doesn't do anything, and there's nothing, it's actually done. So nothing gets missing. And for the filter, then we'll see that's how missing elements, I mean, going in. So if the function, if predicate on Y returns true, then we pass the element to the continuation. And if it returns false, then, well, we do nothing. So looking at this, there are no, of course, sum and none, and there is no deconstruction and deconstruction, repeated deconstruction of sum and nones. So which kind of good, but if you look closely, the things actually, I mean, get even worse. Because, for example, it looks at the map. So we see that every time that this function is invoked, that the closure is created, because this is a functional composition, so it creates a closure. So create a closure on each for each element. So it's actually got worse. So we still, well, the closure is creating, of course, closure is a, I mean, on a fixed data structure, so it's not unbounded, but typically the closure is bigger than some value. So things actually get worse. Well, I mean, I know it's very common that because before things get better, they get worse. But at least in here, things do get better. And how do we, improve things? And is that we say we don't actually want to compute things right now. We wanted to compute, generate code. And so I define the data type of a code, which is an expression that represents the generated code, which in this case could be just a string. So the type array change the representation. So instead of having the value, the length of the array now and the indexing function that takes the index now, it takes the code of, it has the code of the length. And function to array is actually shows, it's very clear. So that was to array before. So it has a array and it creates the general array using the length of array and indexing function. Then when it's invoked, gets, takes the element of this array and passes the continuation. That was how before. What we do now is, well, now we get not an array, we get the code of array. Well, for example, name of the variable. And instead of computing length of the array, we just write the code, so we will compute the length of the array when we run this code. So you're not doing it, but doing it now, but putting it later. And now the indexing function, instead of getting the index of array, now it says, well, I would generate the code for getting the index array when, in the generated code. So you can see the transition again. So before, now we had computations. Then now, and what we do is we add some quotes, and we had some holes into the codes, and using printf to fill the holes with some code. So like, for example, in here, array length, we put here the hole, and we put in the hole the name of the array. So which is also, string. So which would be the name of which array we compute the length. So here a map was before. Well, surprisingly, map now is has exactly the same body. It's simply, the processing is, we compose update function with the continuation, but the type is different. So the transformer, it's not transforming of the value, it's transforming of the code of the value. So it takes the code and performs whatever needs to the operation to get the transform code. The summation function before, well, we do the same thing as I said, we just put quotes in appropriate places and holes. So put everything in holes, in quotes, and where we need the variables, for example, where we need n, so we get this, and so the length of the array. So, well, the code for the length of array was part of the generalized array data structures as n. And whatever the body of the array, what we are going to do? Well, indexing expression is going to provide this source of elements. And when it gives the elements, then we perform summation. And for filtering, it's very similar. So before we, perform filtering now, and nowadays, now we generate the codes and also add the up for generating application. And what we get, so we had previously this pipeline, so to array and filters flown, and we changed it a little. So the to array I mean, instead of the present stage variable, it would be code of the array, probably variable, and is finite is now applies that, I mean, function that will be existed. Runtime float is finite, and the square is applying the square. And now for this pipeline, we see the code as shown on the slide. So as you can see, there is no longer any intermediate data structures, even constant size. There is no garbage created. And although this is code is in OCaml, it's essentially C code, right? So there is no, I mean, there is no dynamic allocation is needed. There is no, this code can run without any garbage collection. So it's essentially C code. Well, this is the general idea. So of course, I mean, there's many details, and printf isn't the best way of generating code. And I just wrote a paper about it. But, well, you know, this is the general idea. And Streamonos is the library that will further develop this idea. And let me, I mean, I'll show you to the extent this idea can be further developed. So the code that we just saw were very similar code with a filter map square, sum of squares with filtering. So only filters, not instead of nonce, is filters even numbers, is written in Streamonos in the way shown on the top of the slide. So so there is a combinators in two namespaces. So in one namespace, a default namespace, there is a filter map, some int and so forth combinators, which describe the stream itself with a pipeline. And the C namespace, which it's a combinator that generate code. So we can see for example, C for X star X, the star is in the C namespace. So it's not multiplying X and X, it's generate code for multiplying X and X. And here's the code which is generated for it, which is, well, I mean, I know the same code we saw before with some lets and expressions added. A little bit more, I mean, I know, well, very similar example, but so we can write pipelines. For example, iota creates a stream of elements from 1 to, I mean, I know, to without any bounds. Then we can square the elements, and we can write a function for sum these elements, and we can add to the previous pipeline filtering and also the take operation and sum them up. So it generates this imperative code. And as I said, that this code is really, I mean, a C-like code, and it's not just a C-like code, because depending on what C is, what module this C is, it can, Streamonos can generate either this OCaml code, or it can generate C code. So this is the generated C code. So it's, I mean, I don't know, it's truly C-like code, because, and we can truly generate C code. And a little bit more interesting example is database join. So if there is a table 1 that contains strings and int, and table 2 contains int and float, and we perform database join with some filtering, then we can implement in the Streamonos by first computing the Cartesian product, then, well, filter, so performing this join with from T to 1, then where clauses performing filtering, and then performing selection, which is projection, and performing output. And I don't show the output, but the output is standard nested loop join, again, without any intermediate data structure. And there is a weird test. I don't know why it's, I mean, I don't know even wrote it, but it just shows many things that many combinators that Streamonos provides, including there is a zip, and including there's a flatmap, which is actually showed before, and there's a filter even, so there's a zipping of 2 streams, and streams there is a of int array, so there's a finite array, mapping square, take, filter, and there is another iota, which is infinite streams, and it's also mapped with some iota and limited by some elements. And of course, there is a correlation, so that's the iota from which we start depends on the, I mean, element of the outer stream. So this is kind of like, well, I mean, correlation. And eventually all of them zip together. And it generates, very complicated code. Well, especially the last line is probably, kind of puzzling. There is tests which assigned to some. But, well, it's a, why to note, our original Streamonos paper actually couldn't generate such code, and there was some high order function remains. But nowadays we can generate without a high order function, without any closures, and you can see there are some incrementing, decrementing, incrementing, decrementing, and assignment. That's the typical code. And okay, there's some 3 minutes left. So there's Streamonos can also generate operate streams which have state. So, for example, we can write a difference encoder, which takes the stream and computes and outputs the stream with the difference between neighbors elements. So there is we declare a state, and for each, we map the streams, which is mapping from the current element to the what is in the state, and then update the state with the current element. And take while is also can be implemented in a similar way. And to show some numbers, so for Streamonos, there is also the version of Streamonos for Scala, which can generate Java code, well, Scala Java code. And the first line, which is blue, it's the baseline Java, so it's written by hand. And there is a baseline Scala red, which is also written by hand. And then yellow, it's the Java 8 streams. And the last one, green, is the code that we generate. So you can see we can generate basically what written by hand. And Java 8 sometimes, has bad performance. And sometimes it's actually, Java 8 does not support zip. So there are some things missing. And this is for the C code. So probably it's better to look at the orange and red. So because, so the first 2 bars, it's the code we generate. The last 2 bars is the code that wrote by hand. And the green and yellow is compiled without optimizations, and orange and red compiled with optimization. And on the Y is millisecond per operation. So the shorter, the better. So as you can see, we, get basically what, performance of handwritten C code. And very quickly, an example of the FM radio. So this is a standard electrical engineering. It's a real FM radio, but now all the processing steps of the radio are done in software instead of, transistors or whatever. So this is an example of FM radio from William Thiel's PhD thesis, which isn't very readable, but you can, it's also, you can see immediately, although he's from MIT, he is not an electrical engineer, because things flow from top to bottom. So there is a filtering, which it selects whichever bands, then there is a demodulation, and there is a equalizers, which is a series of pass band filters, which multiply with a particular gain and added the two together. And then this is the output. And this diagram also can be also written in Streamonos, well, at least the higher one is in a rather intuitive way. So this is kind of benchmark. So we have some parameters about radio, the sampling rate. So the cutoff frequency, which is the FM radio highest, is 108 megahertz. And so there is a low pass filter, which selects what we are going to station we hear. Then there is a demodulator, then there is equalizer, and well, then there is an output. And all of that essentially is a filtering. So low pass filter is one of the workforces. Other filters are, very similar. So we compute, giving the filter coefficients like rate and cutoffs and so forth. We compute the coefficients of the filter, and then we convert a stream of numbers to the stream of to a stream of windows. So we, chunk the stream in the windows. And then for each window, we perform the dot product with the coefficients. And well, that's how we write the filter. And yes, it generates a very big C code, a very, very long C code. It's kind of, it's about the time. And so in the conclusion is that, so stream processing is a very varied area, from electrical engineering to computer science to MBA and so forth. And fusion is very important and often non-trivial, especially complete stream fusion, where we want to eliminate all data structures, not intermediate data structures, not only unbounded size. And streamonos can do it. And finally, this is the team in which, of my quarters and who worked on this project. Okay, thank you very much.